Hi, what's up everybody? Let's go ahead and go through chapter 33, homework 11, and this is going to be all about electromagnetic radiation, which is more commonly called light. And we're going to look at a few different topics this week, and next week we're going to look at lenses and mirrors, which is an application. So we're going to, again, this week we're going to go through some of the theory stuff. Not a whole lot on the math side that's very heavy. Aside from, I think there's like one or two problems that are kind of intense in terms of the geometry that you have to do. But we just sort of have to define our equations and just know what the different variables mean. And we're going to pull on a little bit from Physics 1 throughout this chapter. So, you know, if you don't know that stuff off the top of your head, that's not going to be that big of a deal. We'll go ahead and recall it as we go here. One sec. Okay, so problem number one has to do with the electric and magnetic components of an electromagnetic wave. So the way that electromagnetic wave works is you have an electric field component that's oscillating in one direction, a magnetic field component that's oscillating in the other direction, and then the actual wave itself is traveling in the third dimension. So we know the way the electric field and magnetic fields can create one another, and so those oscillations are sort of self-reinforcing. But the actual problems that we have to do in terms of that wave are pretty standard, straightforward stuff. We're not actually going to do a whole bunch with the sines and the cosines and the complicated things. So first problem here, we're looking at an airplane and a radio wave from some distance away, and we're given an intensity. The intensity there, the units are microwatts per meter, so pay attention to micro is going to be 10 to the negative 6th. But we just have to do a few quick calculations with the intensity. First thing is they want us to calculate the electric field component from the intensity. Well, the equation that you need to use here is that the intensity is equal to the electromagnetic, or I should say the maximum electric field value, or the amplitude of the electric component of the wave. And so it's that value squared over 2 mu naught times c. Mu naught is the same mu naught we had for magnetism. 4 pi times 10 to the negative 7. C is a new constant for the speed of light, and you can use 3 times 10 to the 8th, I think, to get the most close to the answer that the software is expecting. You might want to use 2.99 times 10 to the 8th, and of course the units, since it is a speed, are meters per second. So that's how you can find the electromagnetic, I should say, the electric maximum, the electric amplitude. For the magnetic amplitude, there's another equation that relates the intensity to the magnetic amplitude. Or what we can do is we can go back to this equation that you may remember from a few weeks ago that I promised would come back. We had this equation that said that the electric field, this is for like the Hall voltage, if you remember, if that rings a bell from the last exam. Remember we had E is equal to V times B. This was when you had an electric field and magnetic field that were canceling out. Well, now we can use this equation also when we're dealing with an electromagnetic wave, because the relationship between the electric field and the magnetic field has to be mediated by the speed of the wave, and the speed of the wave we now know we're calling c. So you could actually rewrite this as the electric field is equal to c times b, and that will be an equation that we can use for any electromagnetic wave. And then our last one is we are given that the radio transmission is radiating over a hemisphere. What does that mean? What's a power? How do we relate a power to an intensity? This goes back to Physics 1 and to a discussion, we had this discussion with sound, and it's that intensity is equal to power over area. The only thing to keep in mind here is, what is the area? Well, the area would be like the cross-sectional area. So if you're radiating over a hemisphere, then your area is not 4 pi r squared. 4 pi r squared is the surface area of a sphere. If it's a hemisphere, that's half of a sphere, then you'd have 2 pi r squared for the area there. And yeah, that's sort of the only coverage of that topic that you'll have. The second problem is going to sort of build off of this. Now we have a cylinder that's levitating. What's going on with the levitating cylinder? Well, in order to levitate, what that means is that you have to have some upward force that's equal to the gravity going downwards. So that upward force we'll go ahead and call the radiation force, or you could call it the yeah, I guess radiation is probably the most straightforward way to refer to that force. And we know we want that upward force to be equal to our weight, and our weight is m times g. All right, so the question is just how do we write down the force for the radiation? Well, I know that I have a pressure, and I can relate the radiation to the force. There's just an equation here. The force is, take it one more step at a time. We know from physics 1, pressure is equal to force over area. So rearranging this then, I want to have a force that's equal to a pressure times an area. Question is, how do I write down the pressure? How do I write down the area? Well, for something, for pressure from an electromagnetic wave, that's called radiation pressure. And there's just an equation for the radiation pressure. It's that it is 2 times the intensity over the speed of light, 2I over c. And then for the area, what is the area that we want to use? We want to use just the area that is exposed, which is just going to be the bottom face of the cylinder. The bottom face of the cylinder is being hit by that upward oriented laser beam. So yeah, so that's just going to be a pi r squared for whatever the r is for the cylinder. All right, so that will be our radiation force, which we'll plug in on the left-hand side. Last thing we want to do is just a little bit of work on the mass, because I'm not going to be given the mass. I'm given some dimensions. I'm given a density, if you recall, from physics 1. Again, we're pulling back to physics 1 quite a bit here. Density is equal to mass over volume. And we can rearrange this and write it as mass is equal to density times volume. And then I just want to rewrite my volume as the surface area times the height. So that surface area, again, we've written as pi r squared over here. So let's go ahead and write it as pi r squared again. And then we'll have times the height that we're actually solving for. And so there you have it. This is just your mass. Keep in mind that we then need to plug it in and multiply it by g. But we'll have this times g will be equal to this guy that we generated over on the right-hand side here in the blue. And if you set those equal, your pi r squareds will cancel out, and you can go ahead and solve for the height. All right, in our next problem, we're going to deal with polarization. So there's one equation for polarization, and the way that this works is you have, if your light is unpolarized and it enters a polarizer, the intensity will be cut in half. And then the, so yeah, from unpolarized light to polarized light, oops. From unpolarized to polarized, your intensity that comes out, which we'll call intensity 1, is just going to be equal to a half of your incoming intensity, which we'll go ahead and call intensity 0, intensity naught. So essentially, what is unpolarized versus polarized? Unpolarized light, the oscillating bits that oscillate perpendicular to the direction the light is traveling, those little oscillating bits are just sort of randomly scattered. A polarizer is like a fence, so I think of it as like a fence, right? Like a slit. And so it's going to orient all of the oscillating bits in one direction. That's why it's called polarized, because all your oscillating bits are just only allowed to oscillate, say, up and down. And so in going from unpolarized random light to polarized light, like you have with your sunglasses, your intensity will be cut in half. Now, once you're going polarized to polarized, you can pass this light through a polarizer. And when you do this, the intensity will be cut down further if there's an angle between your two polarizers. So the equation for that is that your intensity, we'll go ahead and call this intensity 2, will be equal to intensity 1 times cosine squared of the difference in the angles between your two polarizers. So I'm going to go ahead and write that as delta theta. This is the equation that we're using in this case. Now you may notice, since this is cosine theta, since this is rather a cosine function, the zeros of a cosine function occur at 90 degrees, right? So that means that your intensity would be completely destroyed if you ever had an angle difference of 90 degrees. That's very important when we're dealing with polarization. That is just a fact to keep in mind. So in reading our graph, we see that the light is completely destroyed when our middle polarizer is either at 0 degrees or 90 degrees. What that tells us is that the first and third polarizers have to be respectively, one is at 0, one is at 90. We actually don't know which one is which, but that's fine as long as we can say that one is 0 and one is 90. So let's go ahead and just say, without sort of losing anything here, we can go ahead and treat theta 1 as 0 degrees and theta 3 as 90 degrees. And then, and then we just sort of have to procedurally move through each of these polarizers. We know that the intensity of the light between polarizer 1 and polarizer 2 is just going to be a half of the initial intensity. And then we can actually sort of plug this in right here. Our delta theta, in going from 1 to 2, our delta theta from 1 to 2 will be 0 degrees to whatever theta 2 is. Well, they say theta 2 is 44 degrees, so it's actually 44 degrees minus this 0 gives us just another 44 degrees for that delta theta. And then, so again, we'll have 1/2 times the initial intensity times cosine squared of 44 degrees. And then we can just multiply by another cosine squared for our other delta theta. This is the delta theta in going from 2 to 3. Well, if our second polarizer is at 44 degrees and our third polarizer is at 90 degrees, what is the difference between those two? It's going to be 90 minus 44, so it'll just be 46 degrees. All right, so plugging this all together, what are we going to have? We're going to have 1/2 I initial times cosine squared of this theta times cosine squared of this theta. And you can just multiply all of those together. 1/2 times cosine squared of this times cosine squared of that. And that will give you your total emitted intensity. We want as a percentage ultimately, so that just means that we'll divide whatever our final intensity is by I initial. So you'll just essentially divide that out. And you'll get a ratio from doing 1/2 cosine squared, and then you just multiply that ratio by 100 to get a percentage. All right, next up we're going to deal with light that is transmitted through a boundary and something called the index of refraction. This is actually just one equation that we're going to use for the next few problems with some geometry involved. The equation, when you have light traveling from one substance to another, each substance is going to have a different thickness. And so you have this thing called the index of refraction. So moving from one substance to another is called refraction. The index of refraction tells you how much the light is going to bend as it moves from one substance to another. Excuse me. So your equation is just n1 sine of theta 1 is equal to n2 sine of theta 2. And you'll just have the index for the first object times the angle of incidence. Keep in mind that your angle of incidence is measured off of, if this is my barrier between two substances, n1 and n2, I'm going to come in, I have a light ray that does something like this. It'll go bing, just like that. The angle theta is always going to be measured off of the normal line to that boundary. So this would be my theta 1, and this right here would be theta 2. It's going to be more important in a couple problems. In this problem, problem number 4 that I'm looking at, it's pretty explicit what the angles are. And if we move through different materials, so in this one we're going from n1 to n2 to n3 to n4, you actually don't even, as long as all the boundaries are parallel, you don't even need to worry about what happens in n2 and n3, because you just end up with an n1 sine theta 1 equals n2 sine theta 2 equals n3 sine theta 3 equals n4 sine theta 4. So you can just set n1 sine theta 1 equal to n4 sine theta 4, and then you can also set it equal to n5 sine theta 5. And the one thing to note is that since we are in air at the end there, just in case you're not aware, the index of refraction for air is just equal to 1. So your n5 in this problem would be 1, but you're just going to set n1 sine theta 1 equal to n5, which will be air sine theta 5, and solve from there. These problems will get a little trickier as you have more geometry and you have to trace these light rays through, but we don't have to do that just yet. Problem number 5, this is just testing the idea that you have a different angle of incidence for each different color, because each color corresponds to a wavelength, right? Our eyes turn wavelengths into colors. That's why we view them as such. But for this one, they just give you two different indices of refraction for the two different types of light, the two extremes, rather, I should say, the blue end and the red end. And for each one of them, you'll just do, again, n1 sine theta 1 is equal to n2 sine theta 2. And for this problem, we're going from air, so our n1 is air, so that'll be 1. Then we'll have sine theta 1, which they give you explicitly right there, so you can go ahead and plug it in. And you'll set it equal to just your two different values for n2. So they give you like 1.55 and 1.51 or whatever. And you'll just plug in the two different indices of refraction. You'll get two different theta 2's. And then the way that you're going to input your answer, they ask for the angular spread. The angular spread is just the difference between the two theta 2's that you get out. So for each n2, you'll have a different theta 2. One of them will be, they'll be separated by like a degree or something like that. They just want the difference between the two different theta 2's you get from your two different n2's. And then the other part of the problem is say, what is the spread when they exit the other side? Well, we know that we're going from air, where they were not spread apart, back into air. So when you go back into air, you would no longer have an angular spread. There would be no dispersion out there. And so that's actually just a concept question that they're asking about in part B. There's no spread. Okay, problem number 6 is the one that has the geometry, B geometry. And yeah, let's go ahead and I'm going to sort of blow this up and talk through the geometry. I think the geometry here is the most difficult part. The actual, we're just doing index of refraction essentially, but the hard part is getting a ray from one side of this triangle to the other. So here we have a triangular prism. They give us this angle, they call it phi, and we're going to have this ray of light that's going to come in and pass through and come out the other side. All right, and so the tricky part here is getting our angle of incidence here to correspond to some angle out here. So we'll call this, I'm going to call this theta initial and theta final. We're going to have quite a few angles as we work through this geometry, so let's go ahead and set those off initially. Okay, so what I know is that I can do my law of refraction, n1 sine theta 1 equals n2 sine theta 2. I can do it on each end over here to get these two. So we'll go ahead and call this theta 1 and go ahead and call this theta 2. And I know how to do the index of refraction at these 2 points, right? So that'll give me two equations, and I'm pretty sure most people won't have trouble with that. The tricky part is relating theta 1 to theta 2. Okay, so let's step through this. First of all, I know that this angle right here is complementary to theta 1 because theta 1 is measured off of the normal line, so this has to be 90 minus theta 1. And this angle over here has to be 90 minus theta 2. And now what I can do is I can look at this whole thing in here and say, okay, this is a triangle in and of itself, so all of these angles have to add up to 180 degrees. So I just sum up all of these angles, which would give you something like phi plus 90 minus theta 1 plus 90 minus theta 2 is equal to 180. And then you just go ahead and solve this guy. This will just give you a relationship between theta 1 and theta 2, and then you'll use that relationship for the rest of the problem. You'll actually get that, if you solve this, it should be, I think, if I'm doing this right in my head, phi is equal to theta 1 plus theta 2. And so theta 1 and theta 2 will vary. In part A, they want the smallest angle of incidence for which a ray can enter the left face and exit the right face. The smallest angle of incidence would correspond to a final angle over here that's at its largest value. So the largest value would be 90 degrees. So for part A, you'd start off by setting this equal to 90, and then you do the law of refraction, n1 sine theta 1 equals n2 sine theta 2. You do that to find theta 2, and then you plug theta 2 in here and solve for theta 1, and then do one more law of refraction, n1 sine theta 1 equals n2 sine theta 2 to get your theta initial. That's how part A would work. And then we want to have identical angles for part B. That's going to be a little bit more mathematically intensive, but essentially what we're doing there is we're setting theta final equal to theta initial. Let's take a look just at the setup. We know that we're going to have this equation in play. and then we're going to get two different equations over here. So we need our two index of refraction, or law of refraction equations. So we'll have, on the left-hand side, we're going from air. So N1 is air, so that would just be 1 sine of our theta initial is equal to the index for the prism. So I'm just going to write that as n. It's the only n in the problem. The index for the prism times the sine of theta 1. On the right-hand side, we do something similar, where we're going from the prism, which has index n, with a sine of theta 2, and we're passing back out into air. So it'll be equal to 1 sine of theta final. Now, I know that I want the same angle for both theta initial and theta final, so I can replace those both with just some variable. I'd probably just go ahead and call it theta, but you can replace it with whatever variable you'd like. And then the last equation that you're going to have in play is, we know that phi is equal to theta 1 plus theta 2. And since these are identical, we can go ahead and set these equal to each other. And that should give us that we would have essentially the same values for theta 1. Give me 1 second, make sure I'm doing this correctly. What will we end up with there? We should have one sec here. Okay, yeah, I just wanted to double check. I had a longer solution prepared, and then I realized that there's actually a much shorter route, and I wanted to make sure that it works out. It does work out. So yeah, so since we have the same theta initial and theta final, that means that the left side of this equation is the same as the right side of this equation. Therefore, their opposite sides must be equal as well. So we have n sine theta 1 is equal to n sine theta 2. If you reduce that, that means that theta 1 is equal to theta 2. So if you want the angle of incidence and angle of final angle of refraction to be equal, then the internal angles have to be the same as well, right? That sort of makes sense. So these angles have to be equal, and we know that together they must add up to phi, which means that each one of them on its own is just half of phi. So we don't actually have to get too deep into the geometry there, which is nice. All right, next problem is a fiber optic cable. This is just an application of the idea of refraction. This is, again, a geometry problem. We're also using the idea here of a ray that is totally reflected. And what that means is that we want our, when we're doing our n1 sine theta 1 equals n2 sine theta 2, we're doing this law of refraction. We want our ray to be reflected. What that means is that we want the angle over here to be equal to 90 degrees, essentially. This is called the critical angle. And so we set this equal to 90 degrees, and this will give us a relationship between the indices. All right, so to turn that diagram into a two-dimensional diagram, I think is a little bit easier. So we have our, we'll call this our N1, and then we have this sheathing up here, which we'll call our N2, and we have a light ray that's coming in here. It's refracting, and then it is being totally internally reflected right here. All right, so what are our indices? They're already given to us as N1 and N2, and we have 2 points where refraction occurs. One here where we're setting our theta 2 equal to 90 degrees, and then we also have our refraction over on this end, where we'll call this, say, theta 0. And just keep in mind that this angle is actually complementary to this one. If we're calling this one theta 1, in other words, this one has to be 90 minus theta 1. That should be a minus there, 90 minus theta 1. And so you can plug this in when you do your refraction on this side. Essentially, you're going to do this one first with theta 2 is equal to 90. That'll give you a theta 1. And then we'll do 90 minus theta 1 and do another calculation where you have like n0, which is, I believe, going to be air. Yeah, so this will be n0, which is going to be air, so that's going to be 1 times sine of that theta 0, and that'll be equal to n1 sine of 90 minus theta 1. So do your total internal reflection, that's your first calculation, and then for your second calculation, go ahead and do the actual incident. You're kind of working backwards. Do the incident refraction over here on the left side. All right, we got 2 more here. Next problem, oh no, we just have 1 more, it's tight. So the last problem here is problem number 8, and problem number 8 is has to do with, you can have polarization when you have reflection. This is something called, this is related to something called the Brewster angle, and the Brewster angle is just that tangent of theta. We call it theta b for Brewster. It's just named after some guy. And that's going to be equal to just n2 over n1. They give you the n2 is going to be water. So that means that your n1 is, again, going to be air. So that's just going to be equal to 1. And then this will be the index that's actually given as 1.33. And you can solve for your Brewster angle just using this equation. And then part B is just a concept check. Does this angle depend on the wavelength of light? Well, we know that this value is going to be different for each wavelength. If you go back to that where we have the dispersion, the angular dispersion problem with the prism, that was trying to teach us that the index of refraction does depend on the wavelength. And so, yes, of course, you're going to have a different index for each wavelength. All right, and that's it for this week. Next week, we'll get into lenses and mirrors. But it's a pretty straightforward homework assignment this week, and coming down the home stretch. So have a good week, everybody.